So this is a joint work with all these guys. I want to thank my co-authors. I think it's a good place to do it. Thank my advisor and yeah, all the people who are involved in this. Yeah. A short anecdote to like show how flattered I feel actually is Peter Wöller is working here, and I feel extremely flattered to get a prize from this company. Like 5 years ago or something, I asked Peter Wöller all kinds of stupid questions on IRC. I asked stupid questions like, why can't you divide by the curve point, for example? Like, why can't you divide by the generator point? Stuff like that. And he was extremely patient to me, and he made me feel very welcome in the Bitcoin community. And awesome people in the Bitcoin there. So yeah, helpful and like help each other learn stuff. We would have like a free market of sidechains, rollups, and stuff like ZK coins, because that would enable rapid innovation and cheap experimentation. And the things that I'm mostly interested in is in particular scalability and privacy. And yeah, since the base layer is so hard to change, it would be great if we could do that. And the state of the art of like bridging Bitcoin to other layers is yeah, using multi-sig bridges, essentially a T of N assumption, trust me bro, which is not quite nice. Or we use over-collateralized bridges, which are yeah, they come with all kinds of other trust assumptions, and they come with the collateral requirement. And the question is, how do we build better bridges that don't have these drawbacks? And in particular, how do we do that without consensus changes? And people thought that this is impossible, and BitVM is the solution, or a solution to improve on the state of the art. Roughly, the problem that we are trying to solve is we have Bitcoin, and then we have some kind of side system, like a rollup or a sidechain or whatever side system you have. And you want to bridge BTC in there, which is actually not that hard. The problem is that at some point, eventually, someone wants to have their money back. They want to have real Bitcoin back. And that's the hard problem, because at this point, I have to prove to Bitcoin that I'm actually allowed to take money off the bridge. And this is the complicated problem. The trivial solution would be to just take all the blocks of the sidechain and feed it into Bitcoin, and this way convince Bitcoin that I'm allowed to take money out of the bridge. But this would defeat the purpose of scaling, because I have to feed like lots of data into the chain, which is of course not a solution. So what is the solution? Well, snarks. There's hardly any problem in the life of a cryptographer that you cannot solve by a snark. And the same is true with bridges. Snarks enable very efficient bridges, and they are like the hot topic in the entire altcoin world, like all these L2s, which is a huge big topic on Ethereum. They mostly all rely on snarks or starks. And that's why we are so eager, or that's why there was so much interest in having a snark verifier on Bitcoin. The problem is, though, how do we verify a snark in Bitcoin? The problem is Bitcoin script is not really expressive enough. There are all kinds of challenges with Bitcoin script. First of all, we don't have loops. That sucks. We don't have state. It sucks even harder. And we only have very basic opcodes. We can do like these things. I think you all know it. And the big problem is that this is not expressive enough, not even remotely expressive enough to implement a snark verifier in Bitcoin script. We do have some cool opcodes, but they're all disabled, like multiplication, division, and so on. Satoshi went paranoid one day and disabled all of them. And that forces us to build like these crazy Rube Goldberg machines instead of just doing it the clean way with just multiplication and like how people do it in the outcome world. So implement possible. Sad. So can go home. But maybe it is possible. Maybe it is possible. Actually, it's not that hard when you think about it, because there's a simple recipe for how to build a snark verifier in Bitcoin script. We have very highly sophisticated opcodes. If you look very closely, for example, we have addition. We can add two 32-bit numbers, and if we just take a couple million 32-bit additions and add plenty of if statements, and then unroll all the loops that we have to do, and maybe add a few lookup tables to make everything efficient, and then call Liam to like sprinkle a couple of cryptographic tricks on top of that, voila, you got a snark verifier. Great. So it is possible to implement a snark verifier in Bitcoin script. It's actually quite simple. You just have to go through the pain. Pretty cool. Enjoy a snark. But can you really enjoy a snark? Well, there's a catch to it. The size of the snark verifier, well, let's choose Groth 16. Groth 16 is like very popular. Everyone loves Groth 16 who likes snarks. It has like constant size proofs. It's very standard. It has all kinds of great tooling. And it's mostly field arithmetic, but it's like roughly 50K, sorry, it's roughly just modular multiplications. And one of the multiplications is roughly 50K. And we need 30,000 of these multiplications. So in total, we end up with like 1 GB of script. There's a bit of a disconnect here because, as we all know, block size is only 4 megabytes. So we are just like a couple orders of magnitude off here. This is the big problem, actually. Like, we do have our script now, but it's 1 GB, but we only have 4 megabyte. And the question is, how do we fit a 1 GB script into a 4 megabyte block? The question that we try to answer, and the answer to that is BitVM 2. BitVM 2 is a hack to hack like a huge script into Bitcoin and kind of like run it, not really run it, but run it in a way that is good enough such that we can, at the end, verify a snark with it. So that's the rough idea. And what are the key ideas on how to make that possible? Well, first of all, we have seen we can implement a snark verifier in Bitcoin script. We just have to go through the pain. Then if we just had like some kind of state in script, unfortunately, we don't have state in Bitcoin script right now. Bitcoin script is designed to be fully stateless. But if there was some kind of state, then we could apply optimistic computation and then enable efficient falsification. Falsifying an incorrect execution is pretty much as good as actually verifying a correct execution. And falsifying an incorrect result is often easier. A good way to picture that is a Sudoku solution. I give you a Sudoku solution. If you want to check that it's fully correct, then you have to go through all the rows, through all the columns, and like through all the squares, and like check all of them. But if you just want to show that the Sudoku solution is incorrect, it is sufficient to just point out two cells in a single row or in a single column. And if they have the same value, let's say it's both 3 or whatever, then that shows that there is an incorrect column and that disproves the entire result. And that there are ways to disprove something that are much easier than to actually check the correct result. And we are using that to verify our snark or to falsify incorrect snarks. So the first big hack, or like the first ingredient, is like, how do we make Bitcoin script stateful, even though it's designed not to be stateful? And the idea is maybe we can do it with signatures. If we could just verify signatures for arbitrary messages, then we could have like a two-party game where like one party signs, like Alice, she signs a value, let's say X, she sets it to 42 by signing the value 42 transaction in the chain and extract that signature and replay it in the next script and then set the value to X also to 42 because Bob only has a signature for the value 42. He cannot set the value of X to 43 because he doesn't have a signature for 43. And if the script checks that Bob provides a valid signature of Alice, then Bob is bound to the value given by Alice. That's the key idea of how to introduce state with signatures. So Alice signs something, she signs a value, and Bob replays that signature, and his script checks that he provides a correct signature of Alice, and this way he's bound to the value that Alice has set. This isn't like perfect statefulness, but it's like write once, read many. You cannot write twice, because if you have x42 and x43, then Bob can just choose which value he wants to give. So it write once, but that might be good enough for our case, for our use case. The big problem is, though, how do we verify signatures? There is a proposal called opchecksig from Stack, but since soft forks are super hard, we don't have it. And we won't have it anytime soon, probably. So we're stuck. or we are not stuck because they are Lamport signatures. And Lamport signatures are pretty cool because Lamport signatures, they are conceptually very simple. They are so simple. Implement them in Bitcoin script because they require only hash functions. And that means they are quite useful because we can implement them in Bitcoin today, and now we have a signature scheme. The main drawback is that they are extremely large. However, they are small enough to fit into a script, and that means we do have a solution for our problem. Just to give you an idea, for 20 pretty large in comparison to like the 64 bytes for a regular signature, but it solves our problem of having signatures for arbitrary messages. Just to give you a rough idea of how this works, essentially you sign a message bit by bit, and you commit to 2 hashes. You commit to hash 0 and to hash 1, and to sign the message 0, you reveal the preimage of this hash. To sign the message 1, you reveal the preimage of this hash. And that's essentially how a 1-bit Lamport signature looks like in Bitcoin script. And to have an n-bit message, you just copy this n times. So again, the key idea is we do have somewhat stateful scripts now. Yeah? We can introduce script with Lamport signatures. Now, how do we do optimistic computation? Well, optimistic computation, the key idea is don't verify, falsify. We don't check that the result is actually correct. We just disprove incorrect results. And computation is only required in case of a dispute. If somebody provides a correct snark and everybody looks at it and they're like, yeah, that's a correct snark, then nothing happens. Only if somebody is, no, this is incorrect, that's not a correct snark, then they can disprove them. As I said, it's much easier. Oh, I already talked about the Sudoku thing. So how do we actually implement this in Bitcoin script? Well, first of all, we have to understand what taproot and taptrees are. I think most of you know, but I will give a quick rundown. A taproot is actually an address that contains a tree of scripts, and satisfying any of these scripts allows you to spend from that address. And they can be pretty much arbitrarily large, so you can have an infinite amount of scripts in a single address. And each of these scripts can be up to 4 megabytes. So we can have essentially an arbitrary amount of script in a single address. The only constraint that we have is that we can only execute 4 megabytes of this total script. But this is already quite close to what we actually want, right? We can just commit to our huge snark script and we chunk it up into like 4 megabyte chunks, and then we commit to it in a single address. And this gets us already pretty close. Of course, it doesn't really solve it, but we are getting closer. The optimistic snark verifier, how does it work? It's pretty similar to naysayer proof, if you heard of them. The idea is, well, you commit to the snark and also to the execution trace of the verification of the snark. So you run off-chain the verifier of the snark, and then you commit to all the steps of the execution. Of course, this is pretty large, but let's just assume for now we can simply do that. Then we have already enough, because let's say the thing that we want to verify is just f. Like f would be the verifier, x would be some kind of proof, and y would be just true, for example. We can chunk up this function into multiple chunks in the f1 to let's say f1000, and we feed the proof into the first one, and then it produces some intermediate result. Then we feed that intermediate result into the second function, and it produces so on until we get to the end result. And this way we chunk up the computation into small chunks that each produce an intermediate result, and the execution trace is actually all these z's. And now the point is, everybody can look at all these z's, and since they all know these f's, they can just, if it's incorrect, then they can find these that is incorrect. Let's say, I don't know, this is not true, that z1, when you feed z1 into f2, you don't get the z2 that they computed, or that they committed to. Then you can just execute this particular function on chain, compute the correct value for z2, and show that it's not the value that they claimed. Sense? Okay, many people are nodding, but many of you already know how it works. Does it make sense? Or is there somebody who is like, no, it totally doesn't make any sense to me. Please explain it again. Don't be shy. Oh, okay, cool. So the idea is I chunk up the computation into many different, into many small parts. Instead of evaluating the entire function at once, or like the entire verifier at once, I chunk it up into 1,000 parts. And then I make the person who provides the snark commit to the execution trace. The execution trace is essentially all these intermediate results, Z1, Z2, Z3, and so on. And now they have provided these intermediate results, and now I can look at the intermediate results, and if any of them is incorrect, then I can take the last one that is correct. Let's say Z1 is correct, but Z2 is incorrect. Then I feed it into F2 and show that the correct result is not the one that they claimed. And this way I disprove the entire computation because I disprove one step of the computation. Does it make more sense now? Okay, cool. And this is the rough idea how we can do optimistic snark verification. Yeah, in TypeScript, every FI can be up to 4 megabytes. It's 4 GB in total, so we can fit a snark in there. So cool. Now So how do we build BitVM bridges from that, or how do we build Bitcoin bridges? Yeah, we can only verify a snark, but we don't really know how to apply that to actually build a bridge with that. The high-level idea is we would like to bridge BTC to any other system, and the rough idea is that it is kind of fine if the bridge is a little bit clunky. If it's slow and a bit expensive to do bridging, it is kind of fine because end users can just do atomic swaps, and they can just rarely use the chain, or like only large liquidity providers could use the chain, and only for large amounts. It's just important that we have like a trust minimized way to actually get the money back if somebody wanted to have their money back. And as I said, end users can just use atomic swaps. And how we do it is, well, we have some kind of a fixed set of operators. They can operate the bridge, but anyone can be a verifier. And that leads to the following guarantees. But I will, for the sake of simplicity, I will keep it like that. It's still a federation, but a single honest member suffices. So we have a trusted setup, and we can have roughly on the order of 1,000 cosigners for that trusted setup. And let's say we have 100 operators. And the guarantees are, if any of these cosigners here are honest, then the bridge is safe, which means nobody can steal money from the bridge. And as long as one of these operators is live, then nobody can stop a valid packout. So eventually you will get your money back. Even if all the operators are malicious, they cannot steal money from the bridge. Because if one of the cosigners is honest, then the bridge is just safe, and no operator can steal money. And of course, you could become a member. So you could become a cosigner, or you could become an operator. Then you don't have any trust assumptions, because then you are the one that does it. So how do we do that? Well, the next, more state. We already have state with our signatures, but we need more state. We want to encode state in so-called connector outputs. And how does that work? Well, let's say we have some kind of parent transaction here and a conditional transaction. Yeah? We want to make this transaction depend on the condition transaction, which essentially means the conditional transaction can be executed only if the condition transaction is obviously. And we can build this conditional transaction before the condition transaction hit the chain. We can pre-sign that in advance. We can just agree that, like, I can pre-sign this conditional transaction without this transaction being on chain. I just need to know this output. And then we can encode state in there by saying that if this output gets somehow spent by an alternative transaction, then it renders the conditional transaction obsolete, because the conditional transaction also depends on this input, like this input. I present my input and I commit to the other input. So if that input is spent in some other way, this transaction is not spendable anymore. because it commits on the existence of that input. That's the key mechanism. So it essentially means you can execute the conditional transaction exactly if the alternative transaction is not executed. And this way we can encode states in outputs, in UTXOs. And that's the key mechanism behind our bridge design. So yeah, the conditional transaction is rendered obsolete if the alternative transaction gets executed. The bridge design pegs in, let's say, 100 BTC. And before she executes the peg-in transaction, she wants transactions, like an entire graph of transaction. And this graph of transaction will encode the script logic. So how does it work? Well, first of all, she wants some peg-out transaction to be pre-signed. This peg-out transaction gives the money to the operator. That's a simplification. Ideally, the money would to like Bob or whoever owns the 100 BTC at that point. But for the sake of simplicity now, the operator is the only one who can take money out of the bridge. And here we have some such a conditional transaction, and it depends on two inputs. So essentially, the money can be taken out of the bridge if these two inputs exist. So where do these inputs come from? They come from the kickoff transaction of the operator who operates the bridge. So once the operator wants to take money out of the bridge, they execute the kickoff transaction. Then they have to wait 2 weeks before they are able to execute this transaction. And then they can execute the peg-out transaction. But of course, we also need to encode logic. And that's why this connector output is also pre-signed with another transaction, with a so-called slash transaction. And here there's BitVM as like a black box. And if the operator lies, then the watchtower will be able to disprove them. And then the watchtower wins an output that allows them to execute the slash transaction. And this way, the operator cannot execute the peg-out transaction because they're missing this input. Does that make sense? Cool. So this is the rough idea of how we build bridges. Here the BitVM is just a black box. There's that snark verifier in there, or like in the next iteration, like the Garbled Circuits thing, then we will have the Garbled Circuits here. But it's always the same mechanism. The key mechanism is if the watchtower wins, they will win an output which allows them to execute the slash transaction. And if the operator is honest, then basically 2 weeks, the operator can execute the peg-out transaction and get the money. And we have this like n times, like for each operator, we have this entire graph pre-signed. And since we're assuming one of the operators is honest or live, it means eventually there will happen a honest peg-out and the money will get taken out of the bridge. Because the dishonest operator, he will not be able to touch the funds anymore once the slash transaction is executed. There is no way back for them. And the funds shouldn't be stuck, of course. That's why there's like, for each operator, one of these setups. You already said it sounds too good to be true. That's why this slide is maybe the most important one. What are the limitations? Well, the first limitation is the complexity. This, like, people who don't like me say it's a weird Rube Goldberg machine. And
True.
Yeah, I'm not sure what to say against that. There is some truth to that. If we could do better, we wouldn't do it, but it is complex. And the other thing is we have to balance the incentives. There's that thing, like if somebody lies, then they should get disproven and they should pay for getting slashed. So if the operator lies, then they should pay the party who disproves them to execute this slashing transaction. And as we have seen, the transactions are like up to 4 megabytes. So they're quite large, and that means the operator has to put up quite a big bond to incentivize other people to execute the slash transaction if necessary. However, what's cool, as long as the incentives are balanced, then there is no reason to try to cheat, and then the money is not needed. Yeah, you don't have to spend it; you just have to put it up. And another problem is that the operator has to front the capital for 2 weeks, and yeah, users have to pay fees for that because it's expensive. And another problem is that there is a liveness assumption, because for every peg-in, all these 1,000 cosigners have to pre-sign about 100 peg-out transactions each operator. And that also means this federation can censor peg-ins. And of course, there's a liveness assumption for peg-ins. Nobody would lose money, like no money would get stuck, but you cannot peg in new money into the side system. Summary, BitVM enables trust-reduced bridges for L2s. It requires no soft fork. The limitation is it's practical, but pretty clunky. And like the first implementation is actually completed. Like we have implemented all of this. People have already, like Babylon has run a test run on mainnet, so it does execute. We even have completed a security audit. And big question, when mainnet? Soon. Don't ask me, I'm not building an L2 on top of that, but Ekram is here. They are probably he can confirm. I don't know how much time I have. Yeah. Hope you guys haven't fallen asleep yet, because this is actually the interesting thing. Yeah, this entire BitVM thing has attracted a lot of venture capital, and that attracted like a lot of research to the BitVM world, and that advanced the research around it pretty quickly. Like it's even for me, it's hard to keep up with everything. And the cool thing is, like, now we have a solution for some of the biggest pain points of BitVM 2, and it's called Garbled Circuits. How does it work? Well, the bridge consists of two parts. We have that snark verifier that I've showed to you, and then there's that bridge contract that I showed, like with a conditional transaction and so on. And the garbled circuits, they make the snark verifier more efficient. The bridge contract essentially stays the same, but the snark verifier is like basically garbled circuits I drop in replacement for that complicated disproving scheme that I showed to you. So roughly the formula is you take the BitVM bridge contract, throw in a garbled circuit for a snark verifier, and then you get like BitVM 3. And the comparison, why is everyone so excited about it? Well, in BitVM 2, it was pretty painful that this assert transaction, where you had to assert to the proof and also to the execution trace, it was, even after we've optimized it a lot, roughly 2 megabytes. And in this like huge tree of disprove transaction scripts, the largest script was up to 4 megabytes. So in total, you had to be able to execute 6 megabytes of script on chain, which is of course very, very expensive, in particular, worst case for like a very high fee environment. That's one of the biggest pain points which made BitVM 2 very challenging in practice. And now, how do garbled circuits work? Or like, how do they perform? Well, they bring down the assert transaction to roughly 8 kilobytes. Requires some Liam magic, but then we get it down to 8 kilobytes indeed. And the disprove transaction is just on the order of 200 bytes. So in total, we are down to 8 kilobytes, and this is like on the order of 1,000x improvement. And that's why everyone is super excited about BitVM 3 now. It's quite funny, like I was at MIT Bitcoin Expo, and Ekram and I, we were scribbling and like coming up with like better bridge graphs, and then Jeremy Rubin came around, and he was like, hey, do you actually know the garbled circuits thing? And then he told me like sentences, and then I was like, okay, BitVM 2 is obsolete. And that was like right after we completed the implementation and just had signed a contract for auditing. It took him like 3 sentences to make a year of work obsolete. But we are thankful. It's a pretty good improvement. In particular, the operators, they are happy because they have to provide way less capital now. So how does it work? The key idea is a conditional disclosure of secrets. So like we agree on some kind of black, and now you can feed a snark proof in there. And if it's incorrect, then this black box reveals a secret. So we have some kind of setup, and there we agree on this black box, which is the garbled circuit. And then at some point, this assert transaction happens, and then this reveals a snark proof on chain, and then you can read that snark proof from the chain. And then the challenger can feed that snark proof into the garbled circuit. And if the snark is incorrect, if the verification function returns false, then this black box reveals a secret. And knowledge of that secret is a fraud proof. This black box reveals the secret exactly if the snark is incorrect. If the snark is correct, then the black box doesn't reveal the secret. So if you know the secret, that means I showed you an incorrect snark. And this is, of course, orders of magnitude cheaper to prove to the chain, because you can easily prove to the chain that you know that secret. That's much cheaper than executing a huge script of like 4 megabytes or whatever. So this is the key idea, and that's what makes it so powerful. How does it work? Well, the rough idea is like, if we know how to garble a single gate, then we probably also know how to garble an entire binary circuit. We probably all have seen, and we love these truth tables. This is A and B equals C. And probably you have all seen something like that. Well, shall I quickly explain? Everyone knows that this is a truth table for A and B equals C. And now how do we garble it? Well, we replace all the values with labels. You've seen where previously there was a 0, now there's A0 here. And where there was a 1, there is A1 here. And same for here. And these secrets are just like random data. And in the beginning, I only know that. It's always a two-party thing. There's a garbler and an evaluator. Now let's say I'm the garbler. I'm the only one who knows these secrets. But I give you like an encrypted version of these secrets. So we have like some encryption scheme. And for each row, the key thing will be later on, I will reveal some kind of input. So I will tell you A is 0, then I will give you A0. And let's say I will tell you B is 1, then I will give you B1. You won't know B0 because I only gave you B1. This is how I set a value. This is how I set an input value. And depending on which input value I tell you, you should be able to encrypt like the corresponding output value. So if I say, what did I say, A0 and B1, then you should be able to decrypt C0. But you should not be able to only C0. And how do we do that? Well, we just encrypt all the possible output values. So the possible output values are C0, 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 C1. And we encrypt them with the input values. So the decryption key for this ciphertext is and B0. And the decryption key for this is A0 and B1, A1 and B0, A1 and B1. So if I reveal some assertion for A and B to you, you will be able to execute the you will be able to decrypt the corresponding output. Does that make sense? See many people nodding. Somebody not quite sure? Okay, this is the key mechanism. And we can easily see that this is composable because the output is just another secret value, right? It's just such a label, just as the input labels. So let's say there's A, B, and C, and for the next one there's D, E, and F, and then you can just take the output value of C and F and feed it into the next gate. And we just need to have like garbled tables to do that. But in theory, that is like the simple idea behind it. And the big problem here is I need verifiable encryption. It's not just that I encrypt that, I have to verifiably encrypt it such that I can show to you that these ciphertexts that I give you that just look like random data to you actually decrypt if you know the correct inputs. So we need some kind of verifiable scheme, and that's actually what makes garbled circuits. It's the key challenge to garbled circuits, I'd say. As I said, gates are composable. So now we know how to compose, how to garble gates, and we can just compose garbled gates into a garbled circuit. And if I reveal some kind of input labels to that circuit, then you will learn the corresponding output label for that circuit. And you will learn exactly only the corresponding output label to my inputs. And you cannot decrypt any output labels for any output that I have not provided the inputs for. So cool, that means we can just take a snark verifier and turn that into a circuit, and now we can enable essentially a universal computation in a garbled circuit. So we can verify any kinds of computation in a garbled circuit if we can just verify a snark. Yeah, that's roughly like the signature. You have like some verification function and you feed in a proof and then it returns true or false. And if you learn the false label, that's the fraud proof. So the rough protocol is during the setup, you agree on a garbled circuit. Then the bridge operator publishes in that assert transaction that I showed you. And then any challenger can read these inputs and feed it into the garbled circuit off chain. And if the snark is false, they learn the output label for false, and that is the fraud proof, which allows them to slash the operator. So what are the challenges of this? It sounds extremely cool. Now everything is great. Not quite. If you do it naively, a snark verifier for a gross 16 proof is on the order of 10 billion gates. That's a lot of gates. And the off-chain costs can be quite big because the circuit can be quite big. I think the first version was like on the order of almost a terabyte or something, down to like, I don't know, 50 gigabytes or so. But that was, Liam did some Liam magic and came up with the Glock scheme and reduced the off-chain cost to like 100 megabytes. The other thing is you actually have to garble that circuit. You have to compute the garbled circuit off-chain. You not just have to garble the circuit, you also have to prove the validity. As I said, you need like verifiable encryption. And if you have to do verifiable encryption for on the order of 10 billion gates, that's a lot of verification, proving that you have to do. And yeah, there are different schemes to do that. And the other thing is, yeah, there are on-chain costs, and you can make like a few trade-offs, like bigger assert transactions, bigger disprove transactions, and then you can reduce the off-chain cost. It's a trade-off space. And of course, there are a lot of security assumptions. Like you can make more aggressive crypto assumptions, and then you get better values in the other properties. Or you could just do trusted computing, which of course makes things more efficient, but also you introduce a trusted party. So you can always make it's a huge trade-off space. And the different solutions that we are discussing, like the first one, which is kind of like the traditional thing, is YAO-style garbling and the so-called cut and choose method for verification. Then there's the Delbreak scheme, which is the scheme that Jeremy Rubin came up with. It comes at the problem, the problem here is that it's cheap to do the proving. However, the on-chain costs are higher. Here, the proving is a bit more expensive. Then a few other schemes I won't. This Liam scheme, which is called Glock, it reduces the size to like roughly 100 bytes, but it also comes with a bit more aggressive crypto assumptions. And there's like lots of research going on. We still haven't figured out what's the best, and it's very exciting to see all the improvements that people come up with. If you're interested in like seeing like what's the state of the art, this paper summarizes most of the methods that we currently know. Outlook. Well, BitVM 3 contracts still have the same drawbacks. They need this covenant emulation. They need this pre-signing committee, and this pre-signing committee is a bit of a problem. So it would be pretty cool if we had a soft fork for input committing covenants. One way to do it is CTV. It's so hacky that like people came up with ways to like actually get rid of CTV. The good way to do it would be TX hash or optx. Introspection opcodes would be another solution. This is actually pretty clean. Another proposal, op template hash, totally doesn't help. It's actually kind of like designed to circumvent the hack that we had been doing with CTV. But in the long term, we would also like to get rid of operators. I like to say BitVM is actually a key workaround to enable things that should actually be possible on the main layer enabled by some soft forks. And the most simple things we could do is just have big int arithmetic. It's kind of like included in Gray script restoration, but ideally we would just do it in simplicity. That would be probably my favorite, and like it would be the cleanest way to actually have a snark verifier directly in Bitcoin. Summary, we're finally done. I'm seeing that people are getting bored. BitVM enables better bridges. It's good for scalability and privacy. BitVM 2 is almost production ready, launches very soon. BitVM 3 and Garbled Circuits are the future. They make things way more efficient, like on the order of 1000x improvement in on-chain cost. The challenges are mostly taming the off-chain costs. And currently many directions are getting explored, and lots of exciting research is going on in this field. And if you're smart enough to research Garbled Circuits, please go ahead and tell us how to solve it. That's it. Thank you.